BYE Boost Your English Episode 46, The Bizarre World of Quantum Physics. Hello, and a very warm welcome back to BYE Boost Your English, the podcast dedicated to helping you master the English language through engaging and fascinating topics. Today, we are diving into one of the most mysterious and mind-bending subjects in modern science, quantum physics. This is a topic that utterly shattered the bedrock of classical Newtonian physics and continues to challenge our fundamental understanding of reality itself. Prepare to explore not just the bizarre science, but the revolution it ignited among the world's greatest thinkers. As a special note for our most curious minds, if you find yourself fascinated by these subatomic mysteries and wish to explore them even further, we have since created a dedicated scientific series called the Matrix Phase. For a deeper, even more technical dive into this precise subject, you can refer directly to part 5 of that series. But for today, let us lay down the essential foundations. Let's boost your English and your scientific knowledge. The classical fallacy and the quantum dawn. For over 2 centuries, the cosmos was a meticulously crafted machine, governed by the predictable clockwork of Newtonian physics. This was a deterministic world where certainty reigned. If one knew the initial state of a system, its future could be calculated precisely. However, at the turn of the 20th century, meticulous scientific observation began to expose profound cracks in this classical edifice. The initial challenge stemmed from the puzzling observation of blackbody radiation. Classical physics predicted that an object should emit infinite energy as its temperature increased, a catastrophic theoretical failure known as the ultraviolet catastrophe. To resolve this foundational crisis, the German physicist Max Planck was forced to introduce a radical, almost desperate, hypothesis in 1900. He postulated that energy was not continuous, but was instead emitted and absorbed in discrete packets, which he termed quanta. This concept of discontinuity was the accidental birth of quantum theory. Later, Albert Einstein expanded upon this paradigm shift with his work on the photoelectric effect, confirming that light itself behaves as though it were composed of these discrete energy packets, which we now call photons. In essence, he demonstrated that the behavior of light was fundamentally linked to its frequency, thus proving the quantization of energy beyond Planck's initial conjecture. These early discoveries were soon cemented by the likes of Niels Bohr, who successfully applied the concept of quantization to the structure of the atom. The Bohr model, though later superseded, was a crucial stepping stone because it stipulated that electrons could only orbit the nucleus at fixed, discrete energy levels. These concepts ushered in a new age, signaling the irrevocable downfall of absolute certainty in physics and introducing a realm governed by probability. The revolution had begun. The unseen rules, superposition and wave-particle duality. Having established the quantifiable nature of energy, we must now delve into the genuinely perplexing behavior of the particles themselves. The quantum realm is governed by a set of unseen rules that fundamentally defy the intuition of our macroscopic world. The first cornerstone of this new physics is the concept of wave-particle duality. Quantum objects are not simply waves, nor are they merely particles. They possess the inherent characteristics of both simultaneously. Light, for instance, can act as a stream of discrete energy packets, the photons, but also exhibits the phenomena of interference and diffraction, which are unequivocally wave-like in nature. The famous double-slit experiment perhaps best illustrates this duality, revealing that a quantum entity chooses to behave as a wave or a particle depending entirely on whether it is being observed. Equally revolutionary is the notion of superposition. In classical terms, an object must exist in a single, definite state. A coin is either heads or tails. However, a quantum particle, such as an electron or a photon, exists in all of its possible states concurrently. Before any measurement is taken, the particle is mathematically described as a combination of all these potential outcomes. It is only the act of observation that forces the system to reconcile this multitude of states and collapse into a single, definitive position or momentum. This probabilistic nature, the reliance on odds rather than absolute certainty, is the fundamental attribute distinguishing the quantum world from our familiar, deterministic reality. The great paradox, observation and the collapse. The core problem inherent in quantum mechanics is the role of the observer. If a particle exists in a superposition of states, what process compels it to settle upon a singular reality? The act of measurement itself is inherently invasive. To measure a property, one must interact with the particle, and this interaction effectively coerces the system out of its multiple quantum states, forcing it to manifest as a definitive particle. This process is termed the collapse of the wave function. Closely related to this phenomenon is the Heisenberg uncertainty principle. This principle dictates that there are pairs of properties, such as a particle's precise position and its momentum, that cannot be simultaneously known with arbitrary accuracy. The more precisely one determines the position, the less accurately one can determine the momentum, and vice versa. It is not a limitation of our instruments, but a fundamental constraint of nature. The most famous illustrative conundrum of this collapse is Schrödinger's cat. This thought experiment places the paradox of superposition on a macroscopic scale, imagining a cat in a sealed box with a quantum device. The device's fate, and therefore the cat's fate, is tied to the decay of a single radioactive atom. Before the box is opened, quantum rules suggest the cat is neither alive nor dead, but in a superposition of both states. This highlights the epistemological difficulty of bridging the microscopic quantum world with the macroscopic reality we inhabit. The accepted resolution to this paradox is often found in quantum decoherence. Decoherence is the process by which a quantum system loses its quantum characteristics, namely, its superposition, due to interactions with the environment. Once a particle is allowed to interact with the vast number of particles around it, its wave function rapidly collapses. This mechanism effectively explains why the superposition of a cat cannot be maintained, ensuring the swift transition from the bizarre quantum world back to the predictable classical physics of our everyday existence. Spooky action, the phenomenon of entanglement. Perhaps the most startling feature of the quantum realm is the phenomenon of entanglement. This occurs when two or more particles become intrinsically linked in such a way that they share the same fate, regardless of the vast spatial distance separating them. Imagine a pair of these entangled particles being spun, like quantum dice. If one were to measure the spin of the first particle and find it to be up, one instantly knows that the spin of the second, even if it is light years away, must be down. Albert Einstein, who fundamentally disagreed with the probabilistic nature of quantum mechanics, famously dismissed this immediate correlation as spooky action at a distance. He believed that such an instantaneous link violated the principle of locality, which dictates that an object can only be influenced by its immediate surroundings, and certainly cannot transmit information faster than the speed of light. However, subsequent research has demonstrated that while the correlation is indeed instantaneous, no actual information or signal can be transmitted faster than light. This concept is termed non-signaling. Crucially, the outcome of the measurement on the second particle remains random. It is only the correlation between the two particles that is definite. The reality of entanglement has been robustly confirmed through experiments based on Bell's inequalities, or Bell tests. These tests provide the mathematical substantiation that the correlations observed in entangled pairs are stronger than any that could be explained by pre-existing or local hidden variables. In essence, these tests validate the non-local nature of reality, a profound conclusion that continues to challenge our most cherished physical postulates. The particle zoo and the search for unity. To gain a truly comprehensive perspective on the quantum realm, one must move beyond the behavior of individual particles and confront the standard model of particle physics. This model represents our best, albeit incomplete, description of the fundamental building blocks of the universe and the forces that govern them. At the core of the standard model lies the concept of quantum fields. Unlike the classical notion of a particle as a discrete, tiny ball, quantum mechanics posits that the universe is made of these ubiquitous, unseen fields. Particles, in this view, are merely localized excitations or vibrations of their respective fields. For instance, an electron is an excitation of the electron field, and a photon an excitation of the electromagnetic field. Within this framework, particles are broadly categorized into fermions, the matter particles, like electrons and quarks, and bosons, the force-carrying particles, such as photons for electromagnetism. For decades, a major piece of this theoretical structure was missing: the mechanism by which fundamental particles acquire mass. This crucial puzzle was solved by the discovery of the Higgs boson. This particle is the quantum excitation of the pervasive Higgs field, which permeates all of space. As particles travel through this field, they interact with it, and this interaction effectively acts as a drag, imparting mass. Without this field, all fundamental particles would be massless, traveling at the speed of light, a profound concept essential to understanding our material reality. Yet, the standard model remains incomplete. It fails to account for gravity and, crucially, for dark matter and dark energy, which constitute roughly 95% of the universe's mass-energy content. This has led to the emergence of highly speculative theoretical particles, such as the dark photon. The dark photon is hypothesized to be a mediating particle for a potential dark force, possibly allowing the ordinary matter of the standard model to interact with the mysterious dark matter, thereby offering a potential bridge to resolve one of the most significant outstanding conundrums in modern cosmology: quantum horizons and speculative theories. The bizarre principles of the quantum world are not confined to the academic drawing board. They are actively being harnessed to forge the next generation of technology. At the forefront of this revolution lies quantum computing. Unlike classical computers that rely on binary bits, 0 or 1, quantum computers utilize qubits, which can exist in a superposition of both 0 and 1 simultaneously. This enables an exponential speedup in processing, promising to revolutionize fields from materials science to drug discovery, and potentially breaking current cryptographic protocols. This threat to security is countered by another quantum innovation, quantum cryptography. By employing the principle of entanglement and the inherent instability of quantum states, secure keys can be transmitted with unassailable security. Any attempt by an eavesdropper to measure the key would instantly collapse the quantum state, alerting the users to the intrusion, a phenomenon often referred to as quantum key distribution. Furthermore, the seemingly abstract world of antimatter has found its way into critical medical applications. The antiparticle of the electron, the positron, is central to positron emission tomography, PET, scanning. In this non-invasive procedure, a radioactive tracer that emits positrons is introduced into the body. When a positron encounters an electron, they undergo annihilation, producing gamma rays which are then detected by the scanner. This precise mapping of biological activity provides doctors with a vital diagnostic tool. Beyond practical applications, theoretical physicists continue the quest for a theory of everything, an ultimate unified framework that can reconcile gravity, described by general relativity, with quantum mechanics. One of the most prominent, albeit highly speculative, contenders for this ultimate truth is string theory. This theory posits that the fundamental particles of the universe are not point-like, zero-dimensional entities, but rather tiny, vibrating one-dimensional strings. The different vibration modes of these strings give rise to all the particles and forces we observe, including gravity. While yet to be experimentally proven, these theoretical contemplations represent humanity's enduring ambition to map the entirety of the cosmos onto a single, elegant mathematical equation. Philosophical aftershocks, interpreting reality. The success of quantum mechanics in predicting phenomena is unparalleled, yet its inherent strangeness has led to deep philosophical divides amongst physicists regarding what the theory actually means. This struggle to reconcile the quantum world with our everyday experience is often termed the quantum interpretation problem, and it directly challenges our deepest assumptions about the nature of reality. The most widespread and historically dominant view is the Copenhagen interpretation, championed largely by Niels Bohr and Werner Heisenberg. This interpretation posits that the wave function, the mathematical entity describing a particle's possible states, is simply a tool for calculating probabilities. Under this view, the attributes of a quantum particle do not exist as definite properties until the moment they are measured. Before observation, they are mere potentialities. The observation itself is what forces the collapse of the wave function into a single, concrete reality. For the Copenhagen school, one should simply shut up and calculate, accepting that the theory is complete without demanding a deeper, intuitive picture of the underlying reality. A striking, though more controversial, alternative is the many-worlds interpretation, MWI, proposed by Hugh Everett. MWI attempts to resolve the paradox of wave function collapse by doing away with the collapse altogether. Instead, it contends that whenever a quantum measurement is made, the universe splits into a multitude of parallel universes, a profound bifurcation. In one universe, the coin lands heads, in the other, it lands tails. Every possible outcome described by the wave function is realized in its own branch of reality. This view is often criticized for its extraordinary ontological cost, the necessity of an infinite number of universes, but is praised for its mathematical simplicity and determinism. Ultimately, these various interpretations represent an ongoing epistemological challenge. They force us to confront the limits of human knowledge and whether our language, honed by the deterministic laws of the macroscopic world, is truly capable of articulating the profound strangeness that underpins the fundamental fabric of the cosmos. Quantum Vocabulary Toolkit. Before we conclude our journey, let's quickly revisit and clarify some of the core terminology used today, as these concepts are essential for C1 level scientific discourse. Superposition, a state where a quantum particle exists in all its possible configurations simultaneously, only collapsing into one upon observation. Decoherence, the process by which a quantum system loses its quantum properties, like superposition, due to interaction with its environment, thus becoming classical. Entanglement, a non-local connection between two particles, whereby measuring a property of one instantaneously dictates the corresponding property of the other, regardless of distance. Locality, the classical principle asserting that an object can only be influenced by its immediate surroundings, which entanglement appears to violate. Wave function, the mathematical description of a quantum system that encapsulates all the possible states and probabilities of the particle. Heisenberg uncertainty principle, a fundamental limit on the precision with which certain pairs of physical properties, such as position and momentum, can be simultaneously known. Blackbody radiation, the electromagnetic radiation emitted by a body absorbing all incident radiation, the puzzle that Max Planck solved by inventing the quantum. Quanta, the fixed, minimum, discrete packets or units in which energy or matter can exist. Fermions, the fundamental particles that make up matter, such as electrons and quarks. Bosons, the fundamental particles that mediate, carry, the forces, such as photons and the Higgs boson. Higgs field, the pervasive, unseen field that gives fundamental particles their mass through their interaction with it. Qubit, the basic unit of quantum information, capable of existing as both 0 and 1 simultaneously, thanks to superposition. Quantum cryptography, a method of communication secured by quantum mechanical principles, making the transmission completely tamper-proof. Positron, the antiparticle of the electron, identical in mass but with a positive charge, used in medical scanning, PET. Annihilation, the event that occurs when a particle collides with its antiparticle, resulting in the conversion of their mass entirely into energy, often gamma rays. Theory of everything, the hypothetical single, all-encompassing, coherent theoretical framework that seeks to fully explain and link together all physical aspects of the universe. String theory, a speculative theoretical framework that posits that all fundamental particles are composed of tiny, vibrating one-dimensional strings. That brings us to the close of this truly mind-bending exploration into the very foundation of the cosmos. From the initial revolution of Planck's quanta to the speculative frontiers of string theory and the philosophical questions posed by the many-worlds interpretation, we hope this journey has challenged your intellect and, more importantly, broadened your command of advanced, technical English vocabulary. Remember, mastering a language at the C1 level requires tackling complex ideas head-on. By engaging with demanding subjects like quantum physics, you are actively developing the nuanced articulation and precise terminology necessary for true fluency. Now that the comments section is officially open on YouTube, I would love to hear your thoughts on this. How do you view reality after exploring these concepts? Do you lean towards the practical shut up and calculate approach, or does the many worlds interpretation feel closer to your own philosophical outlook? Please share your reactions, ideas, and requests in the comments below, keeping our discussion respectful and constructive for everyone in our community. Thank you for tuning in to BYE Boost Your English. If you enjoyed today's deep dive into science, be sure to join us next time. We'll be shifting gears entirely to explore a powerful cultural legacy, the enduring influence of the heavy metal giants, Iron Maiden. Until then, keep challenging your reality and boosting your English. Bye for now.
Boost your English, it's the key. Listen to BYE.